All right. Before I pull up the slide, I want to mention something. So the attendance sheet has some additional questions related to the installation of AutoCAD. So, wrong one. Let me pull up my announcement slides. Actually, give me one sec. There we go. The QR code has it's going to link to the attendance slide. It's going to have some different questions. Specifically, it's going to ask you about whether or not you've been able to successfully install Civil 3D. It's going to ask you whether or not you've had issues, and basically whether or not you would like a virtual machine reserved for you. Some of you who have Mac laptops, I thought there was a Apple version of Civil 3D. There's an Apple version of AutoCAD, but not the Civil 3D. So what I'm going to do to correct that is I'm going to set up some virtual machines on campus that you can remote connect into, but I need to know how many of them, okay? Now, if you have not yet tried to install Civil 3D on your own, it will ask, but I'm going to ask this question again on Wednesday. If you have yet to try to install, please try to get to attempt to install your installation by Wednesday, because what I want to know is how many virtual machines I need to set up. Okay, that's what I'm trying to figure out, because I got to set up one machine for every student that needs the installation. Okay, does that sound good? All right, did everybody get the code? Okay. One other thing, I had a typo on my email because I said homework 8, but I meant homework 7. A few of you seem to have issues uploading homework 7. I don't know why, but I've gotten this from like a handful of you, and I even had 1 or 2 students in my last class mention that. So I'm going to go ahead. I extended the deadline of homework 7 to 5 p.m. And if you aren't able to upload it, or if you have any issues, come see me. Okay? Sound good? Okay. All right. Let's get into vertical curve land. Okay. So today what we're going to do is continue our discussion of construction, as it were, but we're veering away from horizontal curves and we're getting into the land of vertical curves. Okay. All right. So just to make sure, we've been talking about route-based construction for a little bit, and last week what we covered was sort of our considerations from a plan view perspective. So plan view, remember, is in the helicopter looking down, and so what we're trying to do is provide a smooth transition along the road. And so in order to do that, we first lay out straight line segments that intersect at PIs, and then we smooth those curves out by installing horizontal curves. And we're doing that based on design speeds and things like that. Stuff we're not talking about in this class, but we will talk about, or you all will talk about in CE 342. So what I'm getting at is, so like in this class, the radius was given to you. Next semester, you'll be designing that, as it were. Today what we're going to do, and today and on Wednesday, we're focusing on the profile view, on the elevation view. And so what we're focusing on now is vertical curves. Okay, and then next week we'll close this out with the section view, looking at earthwork calculations. Okay, so I want to talk about vertical curves a little bit, and I'm going to break out the dirty word for engineers. I'm going to break out some calculus because I'm going to explain why the equation for a vertical curve is not a circle; it is a parabola. Okay. There is a very specific reason for that, but we're going to talk about the parameters of vertical curves, how to stake them out. So that's what we're going to be doing today. And then on Wednesday, we're going to kind of dip our toes into designing vertical curves, but you'll see what I mean when we get there. Okay, so vertical curves provide a smooth transition from a profile perspective. Okay, so obviously we wouldn't want to be driving around ground profiles that look like this. We would like a somewhat smooth transition along our path. And we have 2 different types of vertical curves that we consider. We have crest curves. So crest curves would be where the grades meet at a point going up, and then sag curves would be where the grades meet at a point below the curve. This is what that would look like in profile view, and to be clear, these are not circles. Okay, these are parabolas. Okay, and I kind of want to explain why. So I am going to break out a little bit of calculus for you. So I want to define the equation of a parabola very, very basically. So the equation of a parabola is maybe going to be something like a plus bx plus cx squared, where a, b, and c are arbitrary constants, right? That's generally what the equation of a parabola is, right? Now, let's break out some Calc 1. Some of you have seen this, some of you might not, but most of you probably have. What is the derivative of this with respect to x? So what's the derivative of that?
0.
What about that?
B.
And this is? There we go. Okay. Okay, so that's going to be the derivative of the equation of a parabola with respect to x. Now, let's make sure we understand what the context is. So I have this equation, but what does it mean? What this will tell you is the slope of the curve at some point x, right? I think everybody's in agreement with that, okay? But now what I'm going to do is take the second derivative, okay? What is the second derivative of this? What's that?
0.
What's this? 2c, okay? All right, so I want to be clear that this is a constant, right? That the second derivative of is a constant. And the context is this is how much the slope or the grade is changing. At x, okay? So using a parabola for the equation of a vertical curve is nice if you want a simple expression that will generate a curve with a constant rate of change of grade, okay? That's why we use parabolas for vertical curves, okay? Does that make sense? Okay. Just so that we are clear, so again, we have crest curves and we have sag vertical curves. One thing that's kind of nice from a vertical curve standpoint is that the vertical curves are stationed from left to right. And so last time, if you remember with horizontal curves, we had to be careful that when we were stationing along the curve, we knew the station of the PI. We had to calculate back to get the station of the PC, and then along the curve to get the station of the PT. Whereas for vertical curves, it doesn't really matter because you're stationing from left to right. So the station from the PI to the PC and the distance from the PI to the PT is the same. So that's kind of nice. So some terminology I do want to throw out to you. So I'm going to throw the terms G1 and G2. G1 and G2 are the grades of the curve on either side. So G1 is sort of approaching the curve and G2 is leaving the curve. And so whenever we're speccing these numbers out, if I give you a positive grade, that indicates we're going uphill. If I give you a negative grade, that means we're going downhill. Okay? So for example, if I were to give you, let's make up some numbers. So if I were to give you G1 is, I don't know, plus 2.5% and G2 is negative 1.8%. What kind of curve am I going to be dealing with? Am I going to be dealing with a crest curve or a sag curve?
Crest.
Crest, right? Because G1 is going to go uphill, G2 is going to go downhill, and so the curve is going to look like that, right? So you can easily determine what type of curve that you're looking at by just looking at the grade numbers, right? Whereas if I were to flip these numbers, then G1 would be going like that, G2 would be going like that, and I'd be dealing with a sag curve. I could do better than that, like that. Does that make sense? So I just throw that out there just to make sure that that's mentioned, because there might be some problem statements where I don't tell you whether it's a crest curve or a sag curve, that you ought to be able to just figure that out by looking at the grades. Make sense? Okay. All right. So whenever we're designing vertical curves, and we're going to dip our toes into this a little bit on Wednesday, but we want to try and handle all of our potential design considerations. So one of the things we'll talk about next week is we want to try and balance our cut and fill volumes across the project. Does everybody have a general idea of what I'm talking about when I say cut and fills? So the idea is that along the staging, along the center line of the project from beginning to end, there might be some areas where we're having to remove earthwork or cut earthwork or cut volumes of earth. And then there's some areas where we might need to fill volumes of earth. But ultimately, we want to balance that. We don't want to have to truck too much fill material onto the site, and we don't want to have to truck too much fill material out of the site. We usually want that to be balanced as much as possible. We do want to provide adequate site distance. This is definitely more of a transportation engineering question. So this is the question so we have two different site distances that we're going to consider. We're going to call those stopping site distances and passing site distances. So stopping site distances is essentially how much a distance you need from point A to point B to stop if you see a given obstruction, and passing site distance is how much distance you need to pass. And that's going to be a variable as a function of the speed limit of the road. Okay, we don't want too big grade changes. We don't want to have a significant rate of grade changes. Sometimes we want to pass through a point of a fixed elevation. That's a little bit of a tricky problem it can be. So for example, if you're designing a curve that's going this way, but you have a road that's going this way or a path that's going this way, then you want the curve to meet at a common point. And so designing the curve for that might be a necessity. Now, usually our design output is curve length based on site distance. I say this value is going to be given in CE 241. But I think on Wednesday we're going to try and dip our toes into seeing how that's computed, and I think you'll find it's pretty easy. I do want to mention some of our notation, and I'm going to just level with you that some of the notation is going to have some very slight differences dependent upon your context. So, for example, if you open up your FE reference manual, the handouts that I gave you last time, the FE reference manual defines the three critical points on your vertical curve as PVC, PVI, and PVT. But most transportation engineers will use the terms VPC, VPI, and VPT, at least in my experience, because that's the notation I believe that AASHTO standardized. So I just want to mention right off the bat that there might be some slight differences in notation. You might sometimes also see BVC or EVC over here, but essentially what we're talking about is the vertical point of intersection, the vertical point of curvature, and the vertical point of tangency. Very much akin to what we did in horizontal curves, just with a V added to it to indicate that we're talking about vertical curvature, not horizontal curvature. Okay? The idea is kind of the same. Whenever we're staking out a vertical curve, typically what we'll do is we'll stake it out at either half or full stations, dependent upon the curve. So I believe on your homework, I'm having you do it at half stations, but you'll see what I mean. Once you know how to do one, it's pretty simple. Again, we're using the equation of a parabola here, and just to sort of indicate, like, so if we go back to math land, okay, so if I throw this equation here, y equals a plus bx plus cx squared, what do these terms mean? So a is your y-intercept. So if I was just in Math 127 or Math 132 land, if I was trying to graph this parabola, what would y, or what would a be? A would be this y-intercept. So for us, a, this constant, is going to be the elevation of the VPC, the elevation of the first point on the curve, okay? B, in this case, B is what we call the slope of the projection line, or really what it is just the slope of the line right at the beginning of the curve. And I mean, I think that's pretty straightforward, because if I looked at the derivative and set x equal to 0, I would get a value of b. So that's my initial slope right here. And so symbolically, this b value is going to be g1. It's going to be the first slope. And then this term c is providing, it's a parabolic constant, it provides the offset down to the curve from the projection line. So that's a little bit more tricky and whatnot, but for the most part, I think you'll see it's a pretty straightforward definition. So for us, the elevation on a point is going to look like this. So this is going to be the elevation on the curve at any random point. Okay, and what it's going to be is, so to compute y, to compute the elevation at some given point, it's going to be the elevation of the VPC plus g1x plus this constant times x squared. Now, a couple things I want to point out. So just about every value that you enter into your equation is going to be in feet, okay? So except for the grades. Now, I want to be clear, the grades that you use for this expression, this is an area where you can kind of, I don't want to say mess up, but this is an area where you might have an error, is that your grades are entered in as decimals, not as percents. So for example, if I gave you a problem and I said that G1 was positive 2.5%, you would use as a value in these expressions 0.025, okay? You would use a decimal quantity, not the percent, okay? Because think about this is sort of like a function, okay? So it's treating it as a number, all right? Does that make sense? Now, if you open up the NCAAS reference manual, you'll find all this stuff here. I mean, you can see the equation of the curve right here. You can find all of the terminology here. Again, same idea. There's a couple of additional things that are in the manual that I'm not really going to worry about so much, like the E value and whatnot, but you can calculate that if you'd like. One thing I will mention, though, is you will see some things here like this G2 and or G2 minus G1 is this capital A, the absolute value of that, or G2 minus G1 over 2L is this lowercase a. So if you see some reference to that in some elements in your textbook or what have you, you'll see where that's coming from. Oh, I did want to mention this term x sub m. X sub m is a nice little shortcut. It will tell you the x value that you need to traverse from the PVC that will get you from the PVC to either the high point or the low point, whether it's a crest curve or a sag curve. You know, so for example, if it's a sag curve, it's a low point. If it's a crest curve, it's the high point. But it'll tell you which what the x value is to get there. So you can compute that x value, take that x value, plug it into here, and get the high point or the low point elevation. Any questions so far? Okay. A couple things. So again, this is a lot of stuff where I'm just trying to really hammer this in. Again, vertical curves, they are parabolas. They're not circular curves like they were with horizontal ones. We do reference the lengths in the horizontal plane. So we're not stationing along the curve. We're sort of just stationing along the x-axis. So it actually makes that part pretty easy. And so we primarily use curve designs where the VPI is halfway between this and this. So we had a problem with that with circular curves where 2t didn't equal L. That's not going to be the issue with vertical curves. That part's going to be pretty easy. The other thing I do want to mention is the process by which vertical curves are staked. Typically, it's done usually in kind of a two-step process. So for example, what I'm looking at right here is a station along a given route-based project. So this is the samurai sword or the lightsaber, if you're a sci-fi fan, through the road. And so what we're seeing here is this would be along the path of the project in and out of the screen. And so typically what you would do is you would install a stake on either end of the cut where the cut's going to begin. So whenever you're doing an earthwork cut, you typically don't cut straight down. You cut that at a slope. Most of you are probably familiar with a 1 to 2 slope. If I mention 1 to 2, would y'all kind of know what I'm talking about there? So we lay that back at a 1 to 2 slope. And then when we start to get pretty close to the bottom, we'll usually go back and install a different stake. But with the second stake, this stake right here in the middle, we're actually driving that such that the elevation of the top of that stake is right there, right where the contractor needs to match in order to meet the specifications of the project. And typically the tops are marked blue, so they're sometimes called blue top stakes. So if you hear that term, if you're ever on a site, that's kind of what they're talking about. Any questions? Let's do a problem. Okay, so I'm going to give you some data regarding a vertical curve. Is this a crest curve or a sag curve? That's a crest curve because it's going up. The first grade is going uphill, the second grade is going downhill. I'm giving you some data about the VPI, and I've got a curve that's 600 foot long. I've got some stuff I want to compute for it, and I'm also going to be using some Excel, okay, to do this. So if you do have your laptop with you, this would be a day to go ahead and break it out because I am going to be doing some Excel calculations. If not, it's not the end of the world because we'll do some of them by hand, but you'll kind of see what I'm about to do here. I am going to show you a couple of nifty tricks regarding number formatting, though, which might make your life a little easier. Okay. All right, so here is our curve, and let's see what we can figure out here. All right, so I have a grade, a G1 of 3% and a G2 of negative 2.4% at a vertex whose station and elevation are 46, 70, and 853.48 respectively. Let's see if we can draw a picture. Because one of the first things that we're asked to do is to determine the station and elevation of the VPC and the VPT. And I don't know about you, but I think pictures would make life a lot easier. Okay, so this first question you can solve without any curved stuff at all. This is just some basic common sense. Okay, so what I'm going to do is I'm going to do this, and so I'm going to indicate a point right here, and I'm going to call this the VPI, okay? Now we're given the elevation of the VPI, and we're given it as, what are we given? We're given it as 853.48, okay? Now we are also given G1 is 3%, and G2 is negative 2.4%. Okay? Now, what I'm going to do is I'm going to do my best to try and be as even with this as possible. Is I'm going to put, let's see, I'm going to do this. Let's do that. I think that'll be good. And then what we're going to do is we're going to try and draw what the curve would look like. So I think the curve would look okay. I don't think you're going to get a better curve out of my horrible art skills than that. I think I was pretty good. Thank you. Okay. Now, the other thing I'm going to do is I'm going to try down here. So maybe what I'll do is I'll sort of like box this in. You're going to see what I'm doing here real quick. And, okay. Okay. I'm going to box this in right here. What is the station of the VPI? What was the station given? 46%. Okay. So one of the things I am going to try and figure out is the station here and the station here. Because this is the VPT, this is the VPC. Now, what were we told about the curve? How long is this curve?
600 feet.
600 feet. Let's also go ahead, let's write down G1, which is plus 3%, but I'm going to write that as 0.03, and then G2 is negative 2.4%, which is negative 0.024. And when we do curve design, you're actually going to get angry at me because in curve design, we actually use the percent. So I apologize. But I have a notation quirk that hopefully helps with that. Okay. So in most vertical curve designs, especially with this one, we are using equal tangent curves. In fact, what you can see here is, so we said this curve here is 600 foot long. I propose that if this curve is 600 foot long, then this distance is 300 feet. And the same thing with this one, this distance is 300 feet. I know my scales are a little off, but bear with me. So if this is 300 feet and this is 300 feet, can somebody tell me what is the station right here? So if this is 4670, what's this station?
4370.
What about this one?
4970.
Okay, all right. So we're getting somewhere. Okay, so this is 43 plus 70, and we'll call this the VPC. And this is 49 plus 70. Bless you. We'll call this the VPT. Okay, so we're figuring stuff out. Now, what I'd like to do is I'd like to figure out what is the elevation of this point and the elevation of this point. Now, I propose to you that you can do that without any curve equations at all. Okay? Let's start off with the VPC. Would you agree the VPC is lower than the VPI?
Yes.
Okay. How far is it horizontally from the VPI to the VPC?
300 feet.
All right. What is the slope of that line between the two?
0.03.
Okay. I seem to remember somebody telling me a long time ago that if you wanted to find the slope, it's the change in y over the change in x. So therefore, the shorthand for therefore, so change in y is m times the change in x. So how could you compute the elevation of the VPC quite easily? How could you do that? Take the elevation of the VPI and do what to it? How about this? How about that? This is the slope of this line times 300. Would that work? That'd get us the elevation of that point, right? Going down at that distance. What is that, by the way? We still recording? Yeah, we're still recording. Because you got to break out that Casio FX115 ES Plus or similar scientific calculator in order to do that calculation. Put a tick mark on there for feet.
850 or 844.48.
844.48. Do I have a second on that? So here, let's rewrite this. Let's do this. How's that? Is that right?
Yes.
So if that's the case, I want you to tell me what is the elevation of the VPT. You tell me. You got your Casio FX115S Pluses. You can do it. I believe in you. I have faith in your abilities as engineering students. How do we calculate it? Just method.
It'd be the elevation of VP1 minus the horizontal distance times the slope.
And the slope is?
Negative 0.024.
Yes. And with both of them, we're subtracting, right? Because it's a crest curve, the VPI is the highest, so both go down. If it was a sag curve, we'd be adding, right? Does that make sense? So what do we get for our elevation of our VPT?
46.8.
Second.
All right, so VPT, hold on, I can write, I promise. 846.28.
Mm-hmm.
Okay, all right. So now we're making something happen, okay? So far, so good? Okay. So, and I'll complete this over here. what I'll do is I'll erase this, and I'll just extend that like that, and I'll erase this and extend that like that, just so we're kind of consistent. And I'll say y VPT. Man, why do I keep wanting to do that as a V again? Is 853.48 minus 0.024 300 846.28 feet. Okay. All right. So far, so good. Okay. Now what we want to do is we want to try and determine elevations for stakes. Okay. So in order to do that, we need to actually use our curve expression, because now what we're going to try and do is we're going to try and determine what's the elevation at 44. What's the elevation at 45, etc. So we're going to actually try and figure that part out. Okay, so let's see what we can see. All right, so in order to do that, we've got to use our curve expression. So that's what we got to use. Okay, so y in this case is going to be, what was the elevation of the VPC? We just computed that. What was that?
844.48.
G1 is 0.03.
Yes.
So plus 0.03x minus, okay, what about G2 minus G1? What is G2 minus G1? It is negative 0.024 minus 0.03. What is that?
Negative 0.054.
Do I have a second? All right. And this is going to be 2 times 600. I don't think I need this parentheses right here. Times x squared. Right? So this is our expression. This is our parabola. Okay? So let's see what we can see. Okay? Station. Okay? So our first station is that one, right? The 43 plus 70, because that's the station of the VPC, right? Then what we're going to have is station 44, 45, 46, 47, 48. I can do better than that. And then we're going to have 49 plus 70. Okay. Now, do I plug these values into this expression? No. Okay. What I plug into this expression are values of x. Okay. And if you remember, so here's the basis for the parabola right here. This is the basis for the parabola. And we're starting our parabola right here, right? This is x equals 0, okay? So I propose that this is x equals 0. Now, how do I determine the x value, let's say, of each of these points? What's the x value of this first point?
30.
And how did you get that?
Station minus station.
Exactly. So we're subtracting our stations from this one. So this one is going to be 30 feet. This one's going to be 130, 230, 330, 430, 530, and 600. Okay? Make sense? All right. Now, let's do y. Okay? Now, first off, this first one, I think that's pretty easy because if I plug and chug x equals 0, that's 0, and I get 844.48. Somebody do the next one. So the next one is going to be that times that. And so what do we get when we chug that out? Oh no, don't tell me. It lost my microphone. We're back. Okay. What do we get for this? Anybody get an answer? We'll say 2 decimal places. 845.34. Do I have a second? Okay. Now, I'm not going to do all of these because I think that's a waste of our time, but I am going to do the last one. I want to do the last one. So this is 844.8 plus 0.03 times 600 minus 0.054 times 600 squared over 1200. What do we get for that? 846.28. Do I have a second on that? Let's make sure. I mean, we should, but this is a verification. Why am I saying should, by the way? Why am I saying that? That was the elevation of the VPT. And we computed that without any curve equations at all. I'm grabbing this chair because I'm going to use this here in a second. I'll show you all some Excel tricks. Did we get that? Okay. Now, I want you as engineers to immediately think to yourself, when you got an expression that you're just going to be doing over and over again, think, nah, we're doing Excel. Okay? So, let's open up some Excel. You don't have to open up Excel with me, but if you have Excel, if you have a laptop with you, this would be a nice exercise to go along with me on this. Okay? So I kind of want to show you some things with this this calculation. I want to show you some Excel tricks that can make your life a little easier. Okay, so the first thing I'm going to do is I'm going to create some cells for G1, G2, and L. And I'm going to say plus 3%, and I'm going to say 2.4%. Now, the nice thing about Excel is that it understands that that's a percent. And so, for example, if you do that plus 1, it knows that it's 1.03 or 103%, right? So you can actually just enter it in as a percent, and Excel will know how to handle that. But you need to use the percent value, okay? So we're going to use 600 feet, okay? So everything that I'm about to do, I'm going to do this problem, but I'm going to do it in Excel, and I'm going to show you some formatting tips and some tricks that can make your life a little easier. Okay, so what were we given at the beginning of the problem? We were given for the VPI, we were given the elevation, which was 853.48, and we were given the station, which was 4670. Now, here's the thing. If I do 46 plus 70, I can do that, but Excel is not going to know how to do math with that, okay? So I'm just going to enter in 4670. I'm going to see later on if I can format that a little bit better, okay? Now, what I'm going to do is I'm going to enter in the elevation right here for the VPC right here. And how did we compute that? We took that Okay, so y'all follow along with me? So I'm using my arrow keys, and I'm saying that minus that times that divided by 2. Okay? So y'all see how I did that? So I'm just going in and I'm just saying, let's calculate that. And when I calculate that, I get this, which is exactly what we had before, 844.48. Okay? I'll leave that up here in case y'all want to follow along with me. Okay? So far so good? Okay. Now watch this. Okay. So I'm going to go up here. I'm going to do station X, Y. Okay. Now what stations did we use? We used station 4370, 4400, 4500, and we did that up until 4970, right? Man, I don't like how that's formatted. I want the station numbers. I want it to look like station numbers. Let me show you how. Watch this. So I'm going to highlight all these numbers, okay? And then see on the home tab, there's the number tab, and see that little dialog box? So I'm going to click that little dialog box. And what this dialog box does is if I go into number, this is all the different ways that it can format a number. Now there's a lot of default ones, but no, I'm going to use a custom one. So I'm going to go into custom, and where it says general, what I'm going to do is you use the number 0, and what I'm going to do is I want you to put 2 zeros, then a plus, then 2 zeros. Okay? So what I'm doing is I'm telling Excel that I want you to format the numbers with 2 digits, a plus, and 2 digits. Okay? So I just went into the format number cell. And when I hit OK, now it formatted it as stations. But I can still do math with it. Okay? Does that make sense? Now, how do I compute my X values? So watch up here. So we say equals that minus that. But do y'all remember how to lock a cell?
Dollar sign.
F4 or the dollar signs. So we hit F4. And so, see, it's automatically spitting it out in stations. I mean, you can just go back up to this drop-down box and change it to general. But, you know, there we go. Okay. Now, what's our equation for the curve? It is the PVC, lock it with F4, plus G1, lock it with F4 times X, plus, then we got a fraction, G2 minus G1 divided by 2 times L, and I need to lock all of that. Anything that's not in this table. So I'm just going to go into my formula bar, highlight all of that, hit F4. Times that squared. Boom. Okay? And then what I do is hit that little corner, double click, bam. Did them all. How do I know I did it right? Last one. Okay. Maybe now what I'll do is I like pretty pictures. So I'm going to go into Insert. And I'm going to go to Insert. Y'all remember how to do a scatter plot from Engineering 111? So you go to your scatter plot. We'll do a curved one since it's, you know, a curve. So we'll go to Insert, Scatter. Let's do this. Okay. Sometimes it'll automatically format. No. So I go into Select Data. Let's get rid of all this hullabaloo. And then here's what I'm going to do. I'm going to add a curve, and for my X values, hold on. Actually, let me move this over here so that I can see what I'm doing. So, select data. Let's get rid of all these. Then we're going to add. Now, what I'm going to do is I'm going to add based on the station. I'm going to do the stations on the X-axis. On the Y-axis, do my elevations. Look at that. I get a vertical curve that's automatically putting station numbers down here because I told it that's how I wanted to format the numbers. And then on the y-axis doing some elevations. So maybe what I'll do is, since I don't have any axis titles, let's put some axis titles down here. Let's call this station. Call this elevation in feet. I don't think we need a legend since there's only one curve. And boom. Now we got a nice little staked out vertical curve. Pretty sweet, isn't it? I mention Excel because I'm going to show you two different curve problems on Wednesday. One of them is a lot easier with GoalSeek in Excel. So I would bring your laptops on Wednesday if you have them, okay? Because we're going to be doing some GoalSeek together, and it will make your life a lot easier, okay? Does that make sense? Okay, I do want to calculate one real quick thing because there's one thing we forgot to do, and that is, if you remember, so let's go through the problem here. What have we done? We did the full station. We used Excel, but we haven't done this one. We haven't calculated the elevation of the high point or the low point, okay? We can do that pretty easily because if you remember, we're given a nice x value that we can just plug in. So this part's pretty easy. So G1L over G1 minus G2. So let's do that. So is this going to be a high point or a low point on the curve? It's going to be a high point because it's a crest, right? So XM is G1L minus G2 minus G1. So this is sorry, oh, G1 minus G2. I got that backwards. Sorry. So that's going to be positive. What do you get for this? Did I typo that in my slides? No, I got that right. I just wrote it down here on the screen wrong. Whoops. So, what do we got for this? I mean, y'all know you have Excel in front of you. It's this big old calculator that'll just do all the math for you. Oh my goodness. 3,000? Is it 3,000 or in the 300s?
No.
Man, this doesn't like me. So Y max is going to be 844.8 plus 0.03 times 333.33 minus 0.054 . And what do we get for that? Anybody got an answer? And I'll show you a way we can gut check it, and then we'll leave. So, anybody got an answer? I'm waiting. Say it again. 849.8. Do I have a second? Okay, let me show you something real quick. So the X was 333.3. That's like really close to station 47. And if you look at station 47, look at what we have here. That's about where the max is, right? So the max matched about where we had that stake anyways. Okay? Does that make sense? All right. I will leave you to it, and I will see you on Wednesday.